Here is a problem on definite integrals, but we're going to make use of the antiderivative to find the answer. By the looks of it, the integrand, which is what we see here, doesn't look anything like what we have in the table, so we have to do a lot of simplification. So let's see if we can simplify this. So let's take the integrand. I'm going to call that f of theta. So f of theta is sine theta plus sine theta times tangent squared theta divided by secant squared theta. I could write that as sine theta over secant squared theta plus sine theta tangent squared theta divided by secant squared theta. So common denominator, secant squared theta. Oh, shouldn't take the common denominator. What do we know about secant theta and tangent theta? We know secant squared theta is 1 plus tangent squared theta. Or is it 1 minus? So secant secant squared theta is 1 plus tangent squared theta. So what we could have done here is, instead of splitting it up, from this step we could have written it as sine theta 1 plus tangent squared theta divided by secant squared theta. And we can use this identity that we just have we can make use of that trigonometric identity and write it as sine theta secant squared theta divided by secant squared theta. Those two would go away and we would simply have sine theta. So that giant expression that we had, so 0 to pi over 3 sine theta plus sine theta tangent squared theta divided by secant squared theta would simply be equal to 0 to pi over 3 sine theta d theta. And that would be f of pi over 3 minus f of 0. Where f of x is the indefinite integral sine theta d theta. From the table, we know that is negative cosine theta. It's not x, this is theta. So f of pi over 3 is negative cosine pi over 3. And that is 60, so negative half. You can use your calculator to get that. And f of 0 would be negative cosine 0, negative 1. Cosine 0 is 1, and there is a negative in the front. So we have minus half, minus of minus 1, which is 1 minus 1 half. So the answer is 1. So here we have an absolute value function, and anytime we have an absolute value function, we've got to know how to split it up. Now recall, a regular absolute value function has a V-shaped and so the vertex point is at 0. So between 0 and negative infinity, the function is decreasing, so negative x. So over there, on the right hand side, the function is increasing, positive x. The same logic sort of applies with 2x minus 1. So where would that tip be, tip of the v? So if you set 2x minus 1 equals 0, we have x is equal to 1 over 2. So the tip is going to be at 1 over 2. So we can define the function f of x is equal to negative 2x minus 1, because this is decreasing and it is increasing there, so the slope has to be negative and positive, for x less than 1/2, and 2x minus 1 for x greater than or equal to 1/2. So we have to split the function at 1/2. We know the properties of integrals. I can split it at half. The function is negative 2x minus 1, and 1/2 to 2, it would be 2x minus 1 dx. So let's say we just have to find the antiderivative of 2x minus 1. And then we could plug in the appropriate numbers. So 0 to 2, absolute value of 2x minus 1 dx would simply be equal to minus integral 0 to 1/2 2x minus 1 dx, integral 1/2 to 2 2x minus 1 dx. So minus f of 1/2 minus f of 0 plus f of 2 minus f of 1/2. Now, as long as I find f of x, I could find the answer. So f of x is equal to integral 2x minus 1 dx to integral x dx minus integral dx 2 times x squared over 2 minus x, which is simply x squared minus x. So f of 1/2 would be 1/2 squared minus 1/2, which is negative 1 over 4. f of 0 is 0 squared minus 0, you get 0. F of 2 is 2 squared minus 2, which is 2. Plug in those values, minus 1 over 4, minus 0, plus 2, minus 1 over 4, distribute the negative 1 over 4, plus 2, minus times minus 1 over 4 is 1 over 4. Get 2 plus 1 half, which is 5 over 2. So which simply would be the area from here to 2. So if 2 is right over there, we're simply adding the area over here to the area over there. And if you find that area, it would equal to 5 over 2. So when we have 2, that would end up being 3. When we plug it in the function. So over here, when we plug in 0, 2x minus 1 would simply give us 1. So a1, a2. So a1 is simply half times base times height, which is 1 over 4. a2 is half times base is 3 halves, height is 3, which is 9 over 4. So the total area under the curve is our integral, a1 plus a2, which is 1 over 4 plus 9 over 4. You get 5 over 2. And you can see that 5 over 2 is the same 5 over 2 we got here. So we are pretty much finding the area under the curve, but in a very easy and nice way. Now, in this problem, it was easy because we simply have triangles. But what if you have a very complex function? We can't be finding area under the curve using the tricks that we did, or using, Riemann sums and drawing infinitely many rectangles to get the answer. It is not productive, which is why we have integrals. So here is another problem which involves the absolute value of sine x. And we go from 0 to pi over 3 pi over 2. Now, what do we know about sine functions? If I could only draw a straight line. Okay, that's good enough. Going to explain the area concept again. So we know the sine function goes from 0 to pi, like so, and then pi to 2 pi, in that manner. So So between 0 and pi, it is just sine x. It's positive. Between pi to 3 pi over 2, it is negative sine x. Right, whatever value sine x that we have, we're going to multiply it by a negative number to get the area below. So what we can do is simply find the area either from 0 to pi over 2 or from pi over to pi and put it between pi and 3 pi over 2. So we're trying to find that area and this area, but whatever area we have for A3 is simply the negative of A1 or A2. But the area is the same. So A3 is equal to negative A1, which is equal to negative A2. It is simply going to be the same. So since we have an absolute value of sine x, there are multiple ways to approach this problem. We can do it as negative sine x between pi to 3 pi over 2, in which case we will have 0 to 3 pi over 2 absolute value of sine x dx is 0 to pi over 2 sine x dx plus integral pi over 2 to pi sine x dx. There will be the exact same minus integral pi to 3 pi over 2 sine x dx. So all we have to do is find the antiderivative, f of x is integral of sine x dx, and we plug those values in, we end up getting negative cosine x dx. Cosine x. Now that is coming directly from the table. So f of 0 now would be negative cosine 0, which is simply negative 1. F of pi over 2, negative cosine pi over 2, which is 0. F of pi is negative cosine pi, which is negative of negative 1, we get 1. F of 3 pi over 2, negative cosine 3 pi over 2, which is 0. So integral 0 to pi over 2 sine x dx would be f of pi over 2 minus f of 0. So we have 0 minus of minus 1, we get 1. Integral pi over 2 to pi sine x dx is f of pi over 2 f of pi minus f of pi over 2 which is 1 minus 0, we get 1. And lastly, integral pi to 3 pi over 2 sine x dx would be f of 3 pi over 2 minus f of pi, which is simply 0 minus 1, we get minus 1. So that is a 1, that is a 2, and that is a 3. And you can see earlier I said a3 is equal to negative of a1 and a2. We can see that happening here. a3 is the negative of a1 or the negative of a2. So I could write integral 0 to 3 pi over 2 sine x dx as a1 plus a2 plus a3, which is simply 1 plus 1 minus 1, we get 1.